we have been looking at linear transformations T from a finite dimensional vector space V to a finite dimensional vector space. So, let us say V is a finite dimensional vector space, W is a finite dimensional vector space, and we have a linear transformation from V to W. We assume that both these vector spaces or vector spaces over a field F. We looked at two fundamental subspaces connected with T. One is R T, the range of T, and the other was the null space of T, which we denoted by N of T. If you recall, we defined N of T to be all those vectors in V which get mapped to the 0 vector in W, and the range of T was all those vectors in W for which we can find a pre-image in V such that T maps the pre-image to B. We defined the dimension of the range of T as the rank of T and denoted it by rho T, and dimension of the null space of T as the nullity of T and denoted it by nu T, and we had the fundamental theorem called the rank nullity theorem. The rank nullity theorem gave us that the rank of T plus the null space of T is equal to the dimension of the domain space V. This is one of the most important theorems for linear transformations, and this gives us many information about how to construct basis for the range of T and the null space of T. We then introduce the notion of 1-1 linear transformations. Once again, let us consider V W to be finite dimensional vector spaces over a field F, and let us take a linear transformation T from V to W. So, T is a linear transformation. So, we have a linear transformation T from a finite dimensional vector space V to W, and we say T is 1-1 if distinct vectors get mapped to distinct vectors. That is, if the two images are same, then the corresponding pre-images must be the same. T x equal to T y if and only if x is equal to y. Then we say T is 1-1. For 1-1 transformation, suppose T is 1-1. Then we already have the 0 vector getting mapped to the 0 vector of W. Any linear transformation maps the 0 vector to the 0 vector. So, we already have the 0 vector getting mapped to the 0 vector. Now, because the map is 1-1, no other vector in V can get mapped to the 0 vector. So, thus we have whenever a image vector gets mapped to the 0 vector, then x must be equal to theta v, because no other vector can get mapped to the 0 vector. This means that whenever T is 1-1, that implies the null space of T must consist of only the 0 vector, because only the 0 vector of V gets mapped to the 0 vector of W. This immediately tells us that the dimension of the null space of T must be 0, but the dimension of the null space of T is what we call as the nullity of T and denoted it by nu T, and hence nu T must be equal to 0. But the rank nullity theorem told us that the nullity of T plus the rank of T is the dimension of V. So, we have nu T plus rho T is equal to dimension of V. This is the rank nullity theorem, and since nu t is 0, we have rho t is equal to dimension of V, and therefore, T is a linear transformation 1 1 from V to W. This implies that the rank of T must be equal to the dimension of V. So, that the rank of a 1 1 transformation is always equal to the dimension of the domain space. The domain space here is V, but the range of T is a subspace of W. So, we have W here, and the range of T is sitting inside that, and therefore, the dimension of the range of T must be less than or equal to the dimension of W. But we have just found that if T is 1 1, the dimension of range of T is equal to the dimension of V. So, the dimension of V must be less than or equal to dimension of W. So, therefore, if the dimension of V is more than the dimension of W, we cannot expect to have a 1 1 linear transformation from V to W. So, thus a priori requirement to have a 1 1 linear transformation from V to W. Recall, we are assuming all are finite dimensional. V to W is that the dimension of V be less than or equal to the dimension of W. If for any chance dimension of V is greater than dimension of W, there is no hope of finding a linear transformation from V to W, which is 1 1. Let us look at some simple examples. Let us take V to be R 3 and W also to be R 3, the usual 3 dimensional vector spaces over the real numbers. Now, let us define a mapping from V to V. Now, W in this case is equal to V. So, we are looking for a mapping from R 3 to R 3. We now define this T as it takes the vector, any vector in R 3 is of the form x 1, x 2, x 3. So, it takes the vector x 1, x 2, x 3, it should take it to another vector in R 3, the new vector that is x 2, x 3, x 1. So, it is sort of a permutation of the coordinates of the vector x. Now, easy to check that T is linear transformation. So, it is easy to check that T is a linear transformation. We have only to see that T preserves addition, that is T of x plus y is T of x plus T of y, and T preserves scalar multiplication, that is T of alpha x is alpha T x. Now, we shall check that T is 1 1. We shall check T is 1 1. What do we have to check? We have to check if T x equal to T y implies x is equal to 1. This is what we have to check. So, let us check that. Now, what is T x equal to T y mean? T x means the vector x 1, x 2, x 3 is taken to the vector x 2, x 3, x 1. T y, the y 1, y 2, y 3 vector is taken to y 2, y 3, y 1. Now, comparing this, we get x 2 is equal to y 2, x 3 is equal to y 3 and x 1 equal to y 1, which implies the vector x is equal to y. Hence, T is 1 1. So, this is an example of a 1-1 transformation. Notice here that the dimension of V is 3 and the dimension of W is also 3. Our requirement, we said that a priori requirement for having a 1-1 linear transformation is that the dimension of V must be less than or equal to dimension of W. Here is a case where we have dimension of V is equal to W. Let us look at another example. Let us take V to be R3 and W to be equal to R4. Notice here that the dimension of V is 3 and the dimension of W is 4. In this case, the dimension of V is strictly less than dimension of W, and it still satisfies the a priori requirement that dimension of V must be less than or equal to the dimension of W. Now, let us define a linear transformation from V to W, that is T from R3 to R4 as follows. What should T do? T should take a vector in R3. So, any vector in R3 is of the form x1, x2, x3. It should map it to a vector in R4. Suppose it maps it to the vector, the first 3 components are the same as the first 3 components of the vector x. Now, it has a fourth component, say, which just sums up the first 3 components. Then once again it is easy to check T is a linear transformation. We shall now check whether T is 1-1. So, is T 1-1? What do we have to check? Again we have to check if T x equal to T y implies x is equal to y. So, let us say T x equal to T y, that implies by the definition of T, that we have here, we have x 1, x 2, x 3, x 1 plus x 2 plus x 3 must be equal to y 1, y 2, y 3, y 1 plus y 2 plus y 3. Then obviously, from this we get x 1 equal to y 1, x 2 equal to y 2, x 3 equal to y 3, which simply means x is equal to y, and hence T is 1. So, thus we can have the possibility exists for a 1-1 linear transformation from V to W if the dimension of V is less than or equal to the dimension of W. We next introduce the notion of an onto linear transformation. What do we mean by an onto linear transformation? Suppose we have 2 vector spaces V and W, finite dimensional vector spaces over a field F, and then we have a linear transformation which maps V to W, T linear transformation. We say T is onto if the image fills up the whole space W. What does that mean? If we take the entire W, then every part of W is the image of some vector in V. What do we mean therefore? What we mean is, for every W in W, there exists a V in V such that T of V is W. This is the same thing as saying the range of T is all of W. Every vector in W is the image of some vector in V. So, the definition therefore is T is onto if the range of T is equal to W. What does this mean? So, therefore, T is onto means range of T is equal to W, the range of T is equal to W. Therefore, the dimension of the range of T must be the same as the dimension of W, but the dimension of the range of T is what we called as the rank of T, and therefore, the rank of T must be equal to dimension of W. So, therefore, we have T is onto implies the rank of T is dimension of W. We also had from the rank nullity theorem, what does the rank nullity theorem says? The rank of T plus the nullity of T is the dimension of V, and therefore, the rank of T, if we add something non-negative, namely nu T to it, we get dimension of V. Therefore, the rank of T must be less than or equal to the dimension of V, because the dimension of V is the rank of T plus something which is non-negative, and hence comparing this statement with this statement, we see that the T is onto implies the dimension of W must be less than or equal to dimension of V. So, an a priori requirement to have an onto transformation is that dimension of W equal less than or equal to dimension of V. Recall that we found that an a priori requirement to have a 1-1 transformation was the other way around, dimension of V was less than or equal to dimension of W. So, unless dimension of W is less than or equal to dimension of V, we cannot expect to have an onto linear transformation from V to W, right. Now, let us look at a simple example. Let us consider the first example we had for 1-1 transformation again. So, we have V equal to R 3 and we take W also R 3 and we define T as x 1, x 2, x 3 going to the vector x 2, x 3, x 1, a permutation of the coordinates. We had this already as a 1-1 transformation, and let us check whether this is an onto transformation. So, clearly to check an onto transformation, we want to see whether every vector in W can be written in the form T of some x in V. So, clearly given any W equal to W 1, W 2, W 3 in R 3, if we define V equal to W 3, W 1, W 2, then we get T of V. What does T do? It permutes the components of V in an order, and when you do that permutation, we get let us see whether we have the W 3. Let us check very carefully. We would like to have the third component to be the first component of the pre-image vector, and the first component to be the second component of the pre-image vector, and so on and so forth. So, if we look at it, we get T V equal to W1, W2, W3. Hence, we have for every W in W, there exists V in V such that T V equal to W. That implies range of T is W, that says T is onto. Let us take another example. Let us take V to be R 4 and W to be R 3. Now, notice that the dimension of V is strictly greater than the dimension of W. Now, we define T mapping V to W as what should T do? It should take a vector in R 4, say x 1, x 2, x 3, x 4. It should map it to a vector in R 3. So, let us say x 1, x 2, x 3. Then clearly it is onto, since for any x is equal to x 1, x 2, x 3 belonging to W, we can take y to be x 1, x 2, x 3, 0 in V and get T y equal to x, and therefore, range of T is W, which simply says T is onto. And as observed earlier, in this case we have dimension of V is greater than or equal to dimension of W. So, now therefore, recall a priori requirement to have 1-1 linear transformation was that the dimension of V, dimension of W was less than or equal to the dimension of V. I am sorry, this is on 2. So, let us summarize both of them carefully. Let us go back and look at what exactly we had. Remember, we had shown that an a priori requirement for 1-1 transformation is that dimension of V is less than or equal to dimension of W. This is what we had. In order to have a 1-1 transformation, we must have dimension of V is equal to dimension of W. So, that is a very important requirement for a linear transformation to exist, that. So, we should have dimension of V should be less than or equal to dimension of W for the 1-1 transformation to exist, and then for onto to exist, the requirement was dimension of W is less than or equal to dimension of V. Consequently, if you want to expect both 1-1 and onto, then you better start with V and W, which both have equal dimension. So, hence a priori requirement to have a linear transformation from V to W, which is both 1-1 and onto, is that dimension of V is equal to dimension of W. Recall the example we had T mapping R 3 to R 3, where we had the permutation of the coefficients or the components. We found T is both 1 1 and on 2. Notice that in this case we have dimension of V is equal to dimension of W. Now, this leads us to a following definition. Let V and W be finite dimensional vector spaces over F, then a linear transformation T from B to W is called an isomorphism of V onto W if T is both 1 1 and onto. So, if you have a linear transformation from a finite dimensional vector space V to a finite dimensional vector space W, which is both 1 1 and onto, then we call such a linear transformation as an isomorphism from V onto W. If such a T exists, then we say V is isomorphic to W. Okay. Now, let us examine this notion of isomorphism a little bit carefully. Suppose V is isomorphic to W, then this says there exists a linear transformation from V to W such that T is 1 1 and onto. Now, we have seen that an a priori requirement for a linear transformation which is both on 1 1 and onto to exist is that the dimension of V is equal to dimension of W. And therefore, if V is isomorphic to W, dimension of V must be equal to dimension of W. Hence, V is isomorphic to W implies dimension of V is equal to dimension of W. Therefore, we cannot expect two vector spaces to be isomorphic if their dimensions are not equal. So, hence cannot expect two finite dimensional vector spaces to be isomorphic if their dimensions are not equal. Now, therefore, the question arises, if the dimensions are equal, can we expect them to be isomorphic? So, the question, if dimension of V is equal to dimension of W, then is V necessarily isomorphic to W? This question arises. Now, before we answer this question, let us look at a very simple property of such isomorphisms from two spaces of equal dimensions. So, a simple property. So, again we start with dimension of V equal to dimension of W, because there is no hope of an isomorphism if dimension of V is not equal to dimension of W, and suppose T is a linear transformation from V to W, a linear transformation. Now, suppose T is onto. When is T is onto? This means if and only if the range of T is W, if and only if the rank of T is equal to the dimension of W, but the dimension of W is the same as the dimension of V. So, if and only if rank of T is equal to the dimension of V, but by the rank nullity theorem, the rank plus nullity is equal to the dimension of V. So, therefore, if the rank of T has to be dimension of V, the nullity of T is forced to be 0. So, the nullity of T must be equal to 0 by rank nullity theorem. Now, the nullity being 0 is what exactly the meaning of the fact that null space of T consists of only the 0 vector, and this is exactly what is the meaning of T is 1 1. So, what we have observed is that if we have two vector spaces of equal dimension, then the moment a linear transformation is onto, it is also 1 1, and the moment a linear transformation T is 1 1 and it is also onto. So, an onto transformation is automatically 1 1 and onto, a 1 1 transformation is automatically 1 1 and onto. Therefore, every 1 1 transformation will become an isomorphism, every onto transformation will become isomorphism. Hence, to check if T is an isomorphism from V onto W, it is enough to check if T is onto or if T is 1 1. Of course, we are assuming that dimension of V is equal to dimension of W. And let us now go back to the question that we raised. The question that we raised was, if dimension of V is equal to dimension of W, are they necessarily isomorphic to W? What does this question mean? This means, can we generate a linear transformation from V to W which is both 1 1 and onto? But now I do not have to worry whether 1 1 and onto, either 1 1 or onto is enough, because one of them implies the other. So, to check isomorphism, it is enough if we check one of them. So, let us go back, that again let us recall that question, recall the question. If dimension of V is equal to dimension of W and both are finite dimensional vector spaces over F, is V necessarily isomorphic to W? This question means, that is, if dimension of V is equal to dimension of W, can we find a linear transformation T from V to W such that T is 1 1 and onto, both 1 1 and onto. Let us see whether we can generate such a linear transformation. So, we are given that the dimension, so let us investigate this, whether we can construct such a T. the information given to us is that V and W are finite dimensional and that the dimensions are equal. So, let dimension of V is equal to dimension of W, let us call that dimension as n. Now, since V is a finite dimensional space and has a dimension n, any ordered basis will have n linearly independent vectors. So, let us choose any ordered basis, let us call it as BV, V1, V2, Vn for V. This we can do because V is a finite dimensional space, its dimension is n, therefore, any basis will have n linearly independent vectors. Similarly, let us choose any ordered basis for W now. The W basis should also have n vectors, n linearly independent vectors, n linearly independent vectors from W. Let us call them as W1, W2, W3, Wn for W. So, now we have these two bases. So, here is V, here is W and we have these basis vectors V1, V2, Vn, W1, W2, Wn. These V's are the basis for V and the W vectors are the basis for W. Now, we are going to slowly generate a transformation from V to W. The way to generate this transformation is a linear transformation is completely determined by its action on the basis vectors. So, we will first say what the linear transformation does to these basis vectors V1, V2, V3, Vn and then decide what it should do for the other vectors in V. The easiest way to do this is to take the first basis vector of V to the first basis vector of W, take the first basis vector, second basis vector of V2 of V to the second basis vector W2 and the last basis vector Vn of V to the last basis vector Wn of W. So, what we do is first we define T as T V1 is equal to W1, T V2 equal to W2 and so on T Vn equal to W. Now, once we have said what T does to the basis vectors, we shall now see what it does to the other vectors. Suppose x belongs to V. If x belongs to V, then any vector in V can be written in terms of the basis vectors as a unique linear combination. So, we should be able to write x as a linear combination of V1, V2 and Vn. Let us do that. So, then x can be written as a unique linear combination x is equal to x1 V1 plus x2 V2 plus xn Vn of the basis BV, of the basis vectors in BV. Now, once we do that, we want to know what is Tx, then Tx should be T of x1 V1 plus x2 V2 plus xn Vn. Now, we would like to have T to be linear. We are trying to define a linear transformation. So, for a linear transformation, T of a superposition is the superposition of the T's, or T of a sum is the sum of the T's. So, we can write this as T x1 V1 plus T x 2 V 2 plus so on T x n V n, since we want T to be linear. Again using the same linearity, T of a scalar multiple of a vector is the scalar multiple of the T of the vector. So, we can write it as x 1 T V 1 plus x 2 T V 2 plus x n T V 1. And we have already said what T V 1, T V 2, T V n are. We said T V 1 we are going to map it to W 1, T V 2 we map it to W 2, T V n we are going to map it to W n. So, what we have got here is that the moment you know the action of the linear transformation of the basis vectors, the action on other vectors is automatically taken care of by the superposition principles. So, thus we have the definition of T as T of V j is W j for j equal to 1 2 n, and for any x equal to x 1 V 1 plus x 2 V 2 plus x n V n belonging to V, T x is by definition is x 1 W 1 plus x 2 W 2 plus x n W. Now, all we will do now is we claim T is linear, and this, see the linear transformation, let us put it. Now, this we have already taken care of in the way we define T, we brought in the linearity to get the definition of x. So, this has already been taken care of. So, we have to going to claim that T is isomorphism. To show T is isomorphism, we have to show that T is 1 1 and onto. We have to show T is 1 1 and onto. And we have observed earlier that when you have dimension of V is equal to dimension of W, you check onto, it automatically forces 1 1. If it is 1 1, it automatically forces onto, and therefore, it is enough to check one of them. And since dimension of V is equal to dimension of W, it is enough to check if T is onto, because the moment it is onto, we know it is going to be 1 1, because dimension of V is W. So, now let us check whether T is onto. Let us look at the definition. If you look at the mapping now, we have W 1 belongs to the range of T, because W 1 is the image of V 1. Similarly, W 2 is the image of V 2. So, W 2 belongs to the range of T, and finally, W n belongs to the range of T. So, we have W 1, W 2, W n. So, we have W 1, W 2, W n all belong to range of T, but these are all linearly independent vectors, and hence dimension of range of T is at least n, because we have n linearly independent vectors in the range of T. But then range of T is contained in W, which is dimension n, and therefore, dimension of range of T must be less than or equal to n. So, comparing these two, we get dimension of range of T must be exactly equal to n, which is equal to the dimension of W. But if R T is a subspace of dimension n in an n dimensional space, it implies range of T must be exactly equal to W, which says T is onto. Hence, T is an isomorphism. So, that what have we achieved therefore? What we have seen we can summarize as follows. You start with a vector space V, another vector space W, both are vector spaces of same dimension, finite dimensions over the same field. So, if we have two vector spaces of the same dimension, say equal to n, then any pair of bases B V, V 1, V 2, V n for V, B W, W 1, W 2, W n for W. So, you start with two vector spaces of the same dimension, take any ordered basis B V for V, any ordered basis B W for W. So, you take a pair of bases, one for V, one for W, leads to an isomorphism of of V onto W as defined above. The isomorphism is obtained by mapping the jth base vector of V to the jth base vector of W. So, therefore, not only that any two finite dimensional vector spaces of the same dimension are isomorphic, there are many isomorphisms that go from V to W. Every pair of bases will give rise to an isomorphism from T to W. So, thus we have any two vector spaces over F having same dimension, we are assuming they are all finite dimensional, having same dimension are isomorphic, and every pair of bases B B for V and B W for W. So, let us say any two vector spaces V W leads to an isomorphism of V on to W. So, what does this all imply then? This all implies the following. Suppose we have a field F. Do we know at least one n dimensional vector space over F? We already know, namely the F n, where you write the n components with the n coordinates coming from F. So, we know that F n is an n dimensional vector space over F. Now, consider any n dimensional vector space V over F. Now, since dimension of V is equal to n is equal to dimension of F n, we have seen that any two vector spaces the same dimension are isomorphic, this implies V must be isomorphic to Fn. What does that mean? This implies there exists a transformation from V to Fn which is linear 1 1 and on to. What does this mean? This means the following: you have V, you have Fn, you can get a transformation T from here which takes any vector x in V to the vector T x in Fn, and this transformation is obtained from T comes from two bases B for V for V and Bfn for Fn. Choose any two bases, one for V and one for Fn. As we have seen earlier, we can construct a isomorphism T from V to Fn. Suppose x is mapped to T x under this transformation. What does that mean? The vector x in V is coded, we can interpret this, is coded or encrypted as the vector T x in Fn. And since T is 1 1, this coding is without any confusion. Distinct vectors get coded as distinct codes, and it is onto means all the codes are exhausted, that is every vector in Fn is an encryption of a vector in X. So, this code is 1 1 and on to, and therefore, there is a translation of the language of V to the language of Fn. All the statements in V can be now translated to the statements of Fn by translating every vector x to its corresponding code in Fn. Now, this translation is actually transliteration, because every word gets translated to a unique meaning, every vector get translated to a unique meaning in Fn. This code is onto, but now in V we are doing some algebra, addition and scalar multiplication, but since T is 1 1, this code also maintains that algebra, because the coded version of a sum is the sum of the coded version. That is what is meant by saying T of x plus y is T of x plus T of y. The coded version of a scalar multiple is the scalar multiple of the coded version. This means T of alpha x is alpha T x. So, this code does not create any confusion, it translates every word uniquely, and every word in the new language has a meaning in the old language, and the translation preserves all the algebra. This means instead of working in V, we could as well work in Fn. So, that which boils down to saying all this means that instead of working in V, we can work in Fn. And once we have worked in Fn, we have got our answers in Fn. Whatever problem is in V, it can be translated to a problem in Fn, and once we have solved the problem in Fn, the answer can be translated back to the language of V. Why can we translate back to that language? This is because T is 1 1 and on 2. So, it will automatically have an inverse map, and that inverse map will carry the decryption part of it. It will carry the coded T x to the original x, and therefore, then finally, we can translate back to V through T inverse which exists since T is 1 1 on 2. Therefore, what this means is the following. It just means that if you have a field F, any vector space of dimension n over F is essentially F n itself spoken in some other language, and for the translation we need this isomorphism, and the dictionary that provides this translation is the ordered basis B V and B W, through which we generate this isomorphism dictionary, and the reverse dictionary is T inverse. T is the translation from V to F n, and T inverse is the translation from F n to V. So, this all amounts to saying that essentially we have to study only F n. Whenever you want to study n dimensional vector spaces over F, the only thing that we have to study are F n, and once we study F n, any other n dimensional vector space can be converted to this language. So, we conclude by saying that thus the only meaningful n dimensional, when we say meaningful means the easiest one to analyze, n dimensional vector space over F is F n, and any other vector space of dimension n over F is essentially F n spoken in another language. The isomorphism is the translation dictionary, and therefore, it boils down to saying we study F n carefully. If you know F n, you know the whole universe of n dimensional vector spaces over F. Therefore, we shall continue looking at F n more carefully. We shall look at this in the next lecture.